Welcome Sunday. I hope you all are enjoying weekends. Some students requested me to make a video on the counter and memory interfacing. So before I start the video, let me talk that we already made some videos on basic concepts. We also made some videos on combination sequential circuits along with practical implications. So you can check out those videos also. And some students mentioned that some queries are also asked or some come to their mind, so I would be more than happy to answer their queries. So we can have a live session, and you can write in the comment box whenever the most of the students or most of the audience are interested to take a live session. So I would be more than happy to answer your queries in a live session, so that your concepts can be more clear, and your doubts can be removed. Okay, so this is Dr. Kamalkant Sharma, your mentor, your guide, your teacher, and more than a teacher, I'm your friend. I just want to clear your doubts about any kind of topic, right? And this is, I think, fifth video I'm making on this digital electronics. So this is counters and memory interfacing. I will break this topic into two videos. We will discuss about counters, and in the later video, in another video, we will talk about memory interfacing and the registers also. So welcome students again. Without wasting time, I'm going to start. So, but when we say counters, today's topic of the lecture of the video is counters and memory interfacing. So when I say counters, I guess what the exact thing come in your mind, that any element, any device which count, right? So but in digital electronics we can count, but as I already told, you can check on my previous video of combination sequential circuit, in which we discussed that we require a clock, because it can be synchronized, it can be asynchronized, it can be mixture of both. It can be considered in a feedback, because memory is considered as a feedback in a sequential circuit along with combinational circuits. So when we talk about counters, we have various classification. Again, there are various definition available in different books. Like if I talk about counters, you don't have to worry about it. You have to understand what counter is all about. So counter, first of all, you have to remember it's not a combinational circuit, because when you're going to count, you are going to discuss or going to consider the past and the present values of the input. And when you talk about past values of the input, you're talking about nothing but your sequential circuit, a memory, which can be temporary, which can be your permanent. Okay. So first of all, you have to understand that what is that. If we talk about counter and flip flop, in counter we're talking about sequence of state. Okay, and over here we are very much emphasize on clock pulse. When I say clock pulse, I already discussed in sequential circuit video that we are having different types of clocks, or three different type of triggering methods. One is event driven, one is pulse driven, and one is clock driven. Over here we are talking about clock. Okay, and in that particular video I also discussed about the pulse and clock. Okay, I gave an example of ECG. If you remember, in ECG we are having a PQRS. Okay, and in this PQRS we can see that they are pulses. We say it's pulse, we don't say it's clock. Okay, so input pulses, yes, they are called count pulses, and maybe clock pulses or originate from external source or internal source, and they need to be periodic in nature. I hope you know periodic, that they have to be occur after regular intervals of time, right? So these sequence of states may follow some binary count, or they can be used in different devices, integration of devices also. So first counter we talk about, that is binary counter. So you can see that we have two states, 0 0, and the next state can be also 0 1. Similarly, if your state is 1, the next state would be 1 1 0. If it is 1 0, the next state will be 1 1, and if it is 1 1, then it would be 0 0. So I hope you understand, this is a clock pulse, or the clock defined. Whenever the clock is there, it would be shifted from 0 to 1 or 1 to 0. So it is working like a switch. So when we talk about binary counter, it follow the binary sequence, and n-bit binary counter. N-bit, I'm again repeating, n-bit binary counter, where we have a counter, we will have n number of flip-flops. So if I'm dealing with 4-bit binary counter, if I'm dealing with 4-bit binary counter, I will have 4 flip-flops that can vary from 0 to 2n minus 1. Now this is very, very important. See students, if I'm making a 4-bit binary counter, I'm going to count from 0 to 7, right? So when I talk about 0 to 7, that means I am counting 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So we are dealing with binary value, but binary counter has some limitations. That is, an n-bit binary counter will consist of only n number of flip-flops with counting from 0 to n minus 1, where n is the same number which we are dealing with. Now I have an example of this binary counter. Here we are talking about the sum trust table. Okay, and the inputs we are also shifting over here. You can see that the 0 is shifting to 0 and the next state would be 1. Similarly, in that case, the input is 1. See, you can see this, consider this input as a clock. If the clock is there, then your next state would be also accumulated or shifted. Now you can see over here, you are having a present and the state Q1 and Q0 as 0, 1. The input is 0, you can say clock is 0. So we are having 1, 0. But wherever the clock is there, it will shift it. 0, 1, the clock is 1, it will be shifted to 0, 0. So that is very, very important. You have to understand this binary counter concept. The binary counter consisting of flip-flop, as I already told you, the flip-flop carries 1 bit of information. I hope this is clear. So basically, broadly, we talk about the counters and we talk about 2 principal categories, in which we talk about asynchronous counter and synchronous counter. Students might, you see my previous video in which I talk about asynchronous counters are event driven. Asynchronous counters are event driven, and the other name of asynchronous counters is ripple counters. Now you can see that in asynchronous counters, the clock won't be same for every flip-flop. And if you are having number of flip-flops, just try to understand. I'm just giving you an overview. I'm not going into detail in the whiteboard or other classroom techniques. But yes, you can write in a comment box if some query is not, if you have any query or something is not clear from the video. When we talk about asynchronous ripple counters, you know the same clock pulse is not given and the first flip-flop is clocked by an external clock pulse and it is going on. That means each successive flip-flop will be clocked by the output of the first flip-flop or the previous flip-flop. Assume I'm having 2 flip-flop and I'm dealing with asynchronous counters. So the output of first flip-flop would act, would act as a clock for second flip-flop and so on. Whereas in synchronous counter, same clock would be given to every flip-flop, irrespective of the number of the flip-flop. We also categorize the counters on the basis of application. Now you can see we have having a ring counter, Johnson counter, decade counter, and up and down counter. You will see yourself these counters have very great significance, great impact. But remember students, these counters, what you are reading over here, what you are understanding over here in the video, they are just the basic counters and you have to understand the basic how the counter work. Now, as I already told you that when we have a asynchronous counter, the flip-flop transition serves and triggering is done by the previous flip-flop, whereas the clock pulse would be given to only one single flip-flop. On the other hand, in the synchronous counter, the clock would be given to all flip-flops. Okay, and the change of the state would depend upon the flip-flop output. I'm again repeating, the change of the state depend upon the previous flip-flop, and triggering, it can be up triggering, rise triggering, or fall triggering. Let's see. I'm using what kind of flip-flop I'm using. You can write in the comment section. I'm using a toggle flip-flop, and if you remember, I discussed in my previous video about the conversion of flip-flops, where we talk about how the T flip-flop can be made from D flip-flop or SR or JK. And anybody can ask you the question, which flip-flop is not looking for any kind of clock pulse? The answer is SR. Okay, it's a latch. And we already discussed the difference between latch and flip-flop. So this is your asynchronous counter. As you can see, the output of this is nothing but controlling the input of other flip-flop. And as you can see the waveform, you're providing a clock, the Q and Q bar is shown over there. They are both inverted to each other, but you can see the clock pulse, okay, which is twice. Now you can see that edge triggering. Now what I try to say about the edge triggering, in a layman language, it is rising and automatically it would go with the rising again. So it's twice of as long. The output will be clock whose period is twice as long. I hope I make it very clear. So when I talk about 2-bit asynchronous counter, that was a single bit. Now if I talk about 2-bit asynchronous counter, best schematic diagram I try to show in a video so that it would be simple and it should be clear to you. The basic concept should be clear to you. You can see we are having two flip-flops. Naturally, they are JK flip-flop, and the J and K value would be very, very high. And we are widening race or race round condition over here. We are giving a clock. Now you will see that's an asynchronous counter. So the output would be Q, and that Q would operate as a clock. I hope this is clear. So in asynchronous counter, why it is known as 2-bit asynchronous counter? Because we are using two flip-flop. Okay. Similarly, you can see when you're talking about Q0 and Q1, the present state of the next state. Sorry. You can see it is starting from 0 is there because it will remain the same state, and then the 1 is there. Similarly, when the Q1 is the next state, it would start from the next rising, next falling edge. I hope this is clear. Now it can be rising triggered or it can be falling triggered. That totally depend upon the type of flip-flop, type of user interface, and the kind of counter you're going to use. As you can see, it is triggered by negative edge of the Q output of the first one. Right? Now again, 2-bit asynchronous counter. So I already discussed, if you remember, students, we discussed about the propagation delay. When I'm talking about propagation delay, it is the difference between input and output. Okay, so you can see the propagation delay should be very minimum, that is desired. But in D flip-flop, we are having a good amount of propagation delay. So you can see that in an asynchronous counter, all the flip-flops cannot be triggered simultaneously. That's why they are producing an asynchronous operation. Otherwise, if they are triggered simultaneously, they would operate in a synchronous way and they would be named as synchronous counter. So what is the algorithm? All the clear inputs are connected together. I would share one video of experiment implementation of this counter using 7-segment display. So you will see that in this, whenever we are going to use IC, all the clear inputs are connected together. Okay, so that one single pulse can clear all the flip-flop. 2-bit triple counters, we require 2 flip-flop. But how many states we have? 2 end state. That is very, very important. Okay, so 2 end state because we are having a Q and Q bar. And number of states in a counter is known as modulus. So normally we name it mod counter. So remember, asynchronous counters are normally named as your mode counter. Like if I talk about 2-bit counter, it is a mode 4 counter because the states are 4. So modulus value, please remember this, most of these questions are being asked in interview and the IES in the Indian Engineering Services and various engineering platform in the placement interviews. They are modulus. They're not interested that you have to draw a modulus counter, but they are interested whether you know what is modulus. Okay, so modulus is basically dependent upon the number of states of an flip-flop. So we can say a 2-bit counter is nothing but mode 4 counter, right? So you can see the most significant flip-flop produces 1 pulse for every n pulses and significant clock pulse, right? So when we talk about 3-bit asynchronous counter, as you can see, I'm using 3-bit asynchronous counter. That means I am using 3 flip-flop. I hope this is clear. Sorry. So if I'm using 3-bit asynchronous counter, that means I'm using 3 flip-flop that is fixed. And the first flip-flop operate, right? The first flip-flop operate, but how it will operate? It will operate depending on the clock output of the first flip-flop would operate at the clock of the second flip-flop and so on. As you can see in a particular timing diagram, the X naught, where the X naught the flip-flop is connected, over there we are providing a clock pulse, right? And simultaneously, that clock pulse would be shifted to another flip-flop through an output of the flip-flop. So we are having X0, X1, X2, where the clock pulse is being provided. And X0 would be a first one, then it would be second one, then we shifted another one. That's how the counting would be carried out. I hope you're clear with the asynchronous counters. Now we are talking about a ring counter, and you can see a different configuration is there. When I talk about ring counter, you can see in ring counter we are using a same clock pulse. So the ring counter is named as your synchronous counter. But the other difference, as you can see in ring counter, the feedback is connected. Okay. So this kind of operation is basically meant for SISO. You will see, we will discuss in register when we are going to discuss registers. You will see we are having different shift registers and SISO operation is being carried out. But the main thing in ring counter is that in this counter, the normal output of the last flip-flop is connected to the input of the first one and the feedback is being provided. Whereas in Johnson counter, you can see this kind of operation is basically your serial in parallel out. You will see in the shift register. When I'm saying serial, that means I'm saying the output of first becoming the input of second, output of second becoming the input of third, and so on. This is serial data. All the clear pulses would be connected together so that single pulse can clear all the previous values. And the feedback loop is given. You can see that parallel data output. Okay. So Johnson counter is also known as twisted ring counter. Now, when I say twisted ring counter, it is exactly the ring counter. Only there is one difference between ring and Johnson counter, that inverted output. You can see the feedback. If I go back, you can see in this, not twisted output is given, not the inverted output is given. The same, I already told you, there are two types of feedback. One is positive feedback, one is negative feedback. And when the output is the same proportion, same character is there with respect to input, we name it the positive feedback, otherwise negative feedback. You can see over here the inverted output is getting feedback or giving back to the flip-flop or the input to the flip-flop. This is your Johnson counter. So if anybody asks you what is the difference, you can easily tell that there is a difference between ring and Johnson counter. So let's discuss now how can we design a counter. I hope everybody is clear. What is the operation? What is asynchronous? What is synchronous? What is feedback? How can we differentiate between different types of counters? Now let's talk about designing of this. So when we talk about counters, now we understand that counters are going to store some kind of information, and they're normally used different types of flip-flop. But one condition is there: the flip-flop should be same. You can use n number of flip-flop, but the flip-flop has to be same. The only requirement, why we do that, why we consider this, why we put this limitation. Assume you are using JK and T flip-flop. In JK flip-flop, we are having two inputs. In T flip-flop, we are having one input. That would be very difficult to manage the operation of different types of flip-flop. Right? So we normally don't prefer, don't recommend. Okay, so n-bit counter having two end states that we already discussed, and two end states as basically modulus. And modulus, if I say modulus n counter, it's the two end states, and varying from 0 to 2n minus 1. Again, I'm using the word cascading. Deliberately, I'm using the using the word cascading, because cascading, you know very well, the output will become exactly the input. Otherwise, in coupling, no, it's not the case. Okay, so that's why due to this mod, because you are dividing the input clock frequency by the mod, and that's why we name it a frequency divider. If I ask you how many this is the exercise I'm leaving to you. How many flip-flops are required for mode 8 counter, mode 10 counter? You can tell me. Okay, and you can reply in a comment section also. So when I talk about classification of counter, I'll discuss that on the basic of asynchronous and asynchronous. In asynchronous, the clock pulse won't be same. In asynchronous, the output of one becomes the second, input of second. In synchronous, it is not the case. Every flip flop would be given in front of you, as you can see in the synchronous way. You are getting an operation, so it is basically a serial output. Yes, and the clock pulse is given. Now you can see that we summarize the differences between the difference between synchronous and asynchronous counter. So you can see that in synchronous counter, with the increased number of state, we are having it is complicated because the clock pulse has to be same. If I talk about the connection, yes, there is no connection, and yes, it is okay, but propagation delay would be very, very less in the case of synchronous counter, where in the case of asynchronous counter it is more, and frequency operation is high. And one condition that need to be followed, that all the flip-flop has to be clocked at the same time, which is not in the case of asynchronous counter. But normally, out of 100%, 99% of the counter follow the asynchronous operation. If I talk about synchronous counter, you can see that up counter, down counter, and a random sequence. What is the algorithm? What is the status? What is the steps we can follow? First of all, we have to calculate how many number of flip-flops we are going to use for a counter. Then draw the state diagram. You can draw the appropriate flip-flop. Minimize, you can use K-map also. And then the circuit diagram logics. Now, one example I'm taking care of, you can see over here. A 3-bit asynchronous counter? No. The difference between a 3-bit asynchronous, 3-bit synchronous counter. Sorry. So 3-bit synchronous binary counter, I'm using T flip-flop. Normally in making counter, we use T flip-flop and D flip-flop instead of JK and SR. So you can see that what I write over here, I write the present state. If you see over here, it is writing from 0 to 7. The next state is starting from 0 to 7 and going back to 0. And in this case, you can see that we are going towards that how that T flip-flop would operate. Okay, so this is very, very important. And the flip-flop T2, T1 and T0, because the clock pulse would be high, T0 would be remain high every time. T1 depend upon the present and the next state, so automatically it is going to change. And similar T2. So you can see the T2 is Q1 into Q0, T1 is equal to Q0, T0 is equal to 1. That is your K-map, already discussed in the basic concepts video. But just remember, in this case, we are having a 3 variables, and 3 variables, we are dealing with triangular K-map. We're not dealing with rectangular K-map. Okay. For this, you can check my previous video of the basic concepts. So when we talk about binary 4-bit synchronous up counters, when it is synchronous 4-bit, so we are going to use 4 flip-flop, that is fixed. Synchronous, that means we are going to use clock pulse. Okay, and we are providing it over here, and different combination or the delay we can provide. So one thing is very, very much clear, that the separate AND gates, we normally use AND gates for transfer information. This is a 4-bit synchronous counter waveform user timing diagram. So I already discussed with you in detail. If you remember, the QA would start from it is 0, it is starting from 1. The next QB, it is 0 0 and starting from 1 again. So that is how we are going to count. Decade 4-bit synchronous counter. When we talk about decade 4-bit synchronous counter, so basically when we talk about decade, we are talking about we're going to count from 0 to 9. Okay, and we are going to count from 0 to 9. It's a decimal number. Decade counter decimal value is 10, you know very well. So after reaching the count of 1001, it backs to 0. So you can see we are going to 0 to 9 and 0. Okay, so it's a synchronous counter. The clock pulse would be given, and we are going to AND gate. This circuit diagram you can derive from the KMAP also. Now we have a 4-bit up down counter. You can see over here. When I'm talking about up down counter, it would be more interesting, students, when you will move to shift registers. When you will see registers, how the registers would operate depending on this operation, the counters. Now, when it is 4-bit up down counter, we are using 4 flip flop. Okay, and the output is be taken out, but it isn't taken out in the parallel mode. Okay, so no feedback is there as such. The last counter that is very, very important. After this, we will only revise the other counters. We are having bidirectional counter. Very, very important counter nowadays. Bidirectional counter, as the name suggests, that these are basically, this can be synchronous also, this can be asynchronous also. And the other name of bidirectional counter is basically universal counter, which can be used for counting up and down. Okay. And when we are going to use bidirectional counter, when there's up and down counter, they're going to count in, and they're capable of counting in particular direction depending upon the sequence, and they can be reversed also. This is the beauty of a bidirectional counter having a different sequence. This we already discussed in counter, but I am again repeating because earlier in the video you saw the ring counter circuit diagram, but now we are going to discuss is working also the ring counter, what is the working of ring counter, how it is going to operate. First of all, it's just a revision of the ring counter for you. Ring counter is a cascaded operation. The flip flop, we normally use D flip flop. As I already told you, in the counters they're going to use D or T flip flop. So common clock signal, all the inputs are going to set and clear. We have to decide the number of states. Number of states would be dependent upon number of flip flop. Then 4-bit counter using 4 flip flop, and number of states would be 4. You can see that over a logic diagram ring counter. It is a 4-bit. Okay, and the condition is 00001, 00000000001, 0010, and 00110. And feedback is already been given. So you can see the truth table of ring counter. Whenever don't need to cram it again. The clock is 0, all the output are 0. When the clock is 1, Q0 is on, all are off. Clock is again 1 after a pulse, after a delay. Then Q1 is on, all are off. Then clock is again 1, so Q2 is on. The clock is again 1 after delay, the Q3 is on. What is the difference? When the clock is 1, due to this feedback, the Q0 will turn on. Right? This is the beauty of your ring counter. I hope this is clear to everybody. This is a waveform of ring counter, and I hope you are clear about it. The waveform ring counter clear would be given to everyone. Clock similarly, it is 00 and then it is 001. See, after 2 clock pulses, after 2 pulses, it is getting started. It is a falling, it is a rising edge. Now you can trigger by the falling edge, but then you have to maintain a pattern. Counter is nothing but a sequence. It can be random sequence also, but it should be follow certain kind of sequence which can be made out. Okay. So like we can see the Johnson counter, again it's a revision of Johnson counter. So another name is twisted ring counters, also known as mode 2 and counters. Okay, number of stage depend on the twice the number of flip flop used. That is very, very important. Okay, so half the number of flip flop we are going to use. Basically the only requirement, only objective is to reduce the number of flip flop. If it is a 4-bit counter, we have to use 4 flip flops, as you can see already in the previous slides. But in Johnson counter, our objective is to reduce the number of flip flops. So you can see the output is connected to the flip flop that we already discussed. It's the theoretical part. So let's go to truth table and the circuit diagram. Now you can see that in the Johnson counter, you can see the 4 flip flops are there. We are giving a 1 clear signal and the inversion is given. Let's see the truth table now. Here no clock is there, so all the outputs are 0. When the clock is there, the same process is started. But when the clock pulse is again given, two clock Q and QB are on. I hope this is clear, because you are talking about QA, QB, QC, QD in a separate day. I am going back to ring counter. You can check out. In Johnson counter, what is the two step we follow? First QA, QB, then it would be QA, QB, QC, and then it would be QA, QB, QC, QD, and then it start QB coming back. I hope this is clear. So it is going in reverse order and a forward order both. So this is how the Johnson counter we talk about. There is a timing diagram of Johnson counter. Okay, this timing diagram is very, very important. CSE students, those are going to read microprocessor or microcontroller in their coming semesters, or if they already have some knowledge about microprocessor, microcontroller, this timing diagram is very, very important to understand. I made it clear in the previous video also, in this video also. So any query you can write in the comment section. Certain application we use for ring counter or Johnson counter, up down counters. Normally I segregate the application in the terms of ring and Johnson counter only. Ring counters are basically used as a frequency prescaler. They also use as crypto analysis. Nowadays we're talking about cryptography, right? They are accumulator counter. We are having a accumulator register in 8085 or in a microprocessor. Over here, I just want to mention there is a difference between microprocessor and microcontroller. Controller is for specific purpose and processor is for general purpose. Similarly, for Johnson counter, it indicates the motion in 2 dimension. It can go with SAIC or FPGA design. You can search out what is FPGA. But if you want to know from my side, it is field process gate array. So frequency of the clock by varying the feedback, and we can use different phase shifting for the ring and Johnson counter. So I am logging off from the counters, but yes, I just summarize what we discussed in this video. We discuss how the counters are made. We discuss the basic definition of counter, why counter is required, what is the classification of counter on the basis of the application and their configuration, what is timing diagram, how the counter works, what are the different counters we have in terms of asynchronous, synchronous, and we also discuss the application of counter, right? So in of extension to this, I will discuss registers and memory in the next video. Okay, so that you can club that, yes, whatever you learned in a counter, that can be easily applied in your practicals. Even though if you want to make any kind of project, you can easily think of that, yes, how this concept of counter can be implicated, can be used in making some memory interface unit. This is all from my side. Dr. Kamalkant Sharma logging off. Thank you. Thank you again. Are available, what the configuration, how they're going to behave, what are the different roles, how can we make a good counter, and what are the different states of counter. We also discuss modulus counter. We also discuss various timing diagrams. We understand what is timing diagram and how can we, understand or make a timing diagram, and what kind of timing diagram is good for which kind of application. So that we discussed in the previous video. We also discussed the application of the counters. I segregate the application for ring and Johnson counter, right? Now we are going to start with another topic, that is your shift register. So when I say registers, I don't know what comes to your mind, but students, when I was studying in engineering and I passed out in the year of 2004, then when somebody told about registers, I was thinking about, what kind of registers they're talking about. Okay, or whether it's my kind of register with a physical register or digital register, because nowadays I'm talking about, see, I entered in this engineering field in the year of 2000. It is 22 years gone, right? And believe me, at that particular point of time, we were not very much dealing with this digital electronics.
I remember I got my phone, that time the Motorola phone were used, and I used that particular phone, and I bought it in the 2003. My father gave to me because I was in industrial training. So what come to your mind? Just write in a comment box. I just want to know what this new generation is thinking about resistors, or what the first thing that come into your mind. Okay. So when we talk about resistors, we are talking about data, because nowadays we are dealing in the world of 5G, right? We require data, and in a very good way. We are not surrendering ourselves to less amount of data. We require data for our social purposes. We want to be social active. We want to do certain work. We are looking for Gmails. So much data, even some Gmail, some providers, some mail provider also stated that they are not in a position to handle this there's a huge amount of data, but still the data has to be understood. Data has to be segregated, diversified. Okay, so when we talk about data, we are talking about registers, we're talking about hard drives, we're talking about memory. And in this lecture, in this video, we will talk about these different type of memories along with registers, along with data transmission, because registers play a very, very important role in data transmission. So without getting more delay, as using delay flip-flop, as we already discussed in the previous video about flip-flops. Okay, so you can check on the previous videos where we discuss about D and T flip-flop. Let's discuss that how the data can be transmitted or transferred from one point to another point. So for this, we are having shift registers. Now, what this shift registers, they are nothing but a kind of sequential circuit. I already made one video on combination sequential circuit. Okay, check it out, students. Shift registers are a kind of sequential circuits and for storage of digital data. But they are comprising of certain flip-flop, and in such a way the output of one flip-flop will become the input of next flip-flop. When I mention this, I'm talking about asynchronous operation that we already discussed in detail, that we are talking about asynchronous operation. So now two functions are been decided or have been accumulated for shift register. One, shift the data within the register or in different registers. It can be left, it can be right. Okay, from right to left or left to right, or it can be bidirectional also. Similarly, store a data. It can be in a serial, in a parallel. If you remember, I discussed in the previous video when I was discussing counters, I was taking an example of serial and parallel output or serial output, what we mean by serial transfer, what we mean by parallel transfer. So there are four modes of configuration in which, or four modes of operation in which we transfer a data or transmit a data or transfer a data. One is serial input, serial output. That means input is serial and output is serial. Very, very good mode of operation, but not that much fast as we require. Then we have serial input, parallel output. Yes, the input output operations are different. So naturally the coordination problem is there, but yes, we use in certain cases. Then we have parallel input, serial out. It is automatically the same. When we talk about parallel, understand, we're talking about a huge chunk of data. When we are talking about serial, we are talking about a train of data. Understand this, right? And the last one is parallel input, parallel output, very fast mode of operation. And normally it is being used in various applications, various devices also. You are using USB, in USB we are using PIPO. Now you can see first mode of operation where we're talking about serial input, serial output. When I talk about serial input, serial output, you can see that I am having a data and a clock. That means I am using D flip-flop. So remember my words, students. I already discussed, already told many times in previous videos. we use D and T flip-flop instead of JK and SR. Okay, and we can convert from SR to D or D to SR or JK to SR or T to SR or D to T. That I already discussed in one of my video. You can check out beta in the video of combinational and sequential circuits. So when we talk about, we are having different stages: stage 1, stage 2, stage 3, stage 4. In the data input, we are having data flip-flop are being used, and this is serial input and serial output. The clock is same, that we are talking about synchronized, and different stages are there. Similarly, with parallel input, parallel serial output, if I go back, you can see in serial input, serial output, the serial input is given, similarly serial output is given. Output is taken out, data output. But when we talk about parallel input, serial output, then we are giving a parallel configuration, as you can see, and the serial output is taken in a very simple way. But that is not recommended. Similarly, this is serial input, parallel output, again not recommended, but yes, you can take it a simple one. Input data is taken out and parallel output is taken from the aligned bit. So the data is transferred also, and you're taking a bit out of this. So Q0, Q1, Q2, Q3. If it's a 4-bit, and if it is a more, you can use the number of flip-flop can be increased. This is parallel input, parallel output. I already told that clear signal would be given to every flip-flop in a synchronized way, so a single pulse can clear all the data, and you are using D flip-flop. I hope this is clear. I go a little bit fast in this shift resistor. Why so? Because we already discussed all this in a previous video. Okay. Now, if you want to know that how the shift register work, then you have to understand two things, students. Now, what are the two things? You have to understand which mode of operation we prefer. Okay. So you have to understand that how this. So when we talk about at serial input, serial output, two things we are talking about. Now in front of you, you can check out. I put two modes of operation which are very much in demand. That is serial input, serial output, and parallel input, parallel output. When I say like this, we are having a data input using a D flip-flop. Okay, and the data is transferred or transmitted to another flip-flop, and the clock pulse is same. So it's a synchronized operation. Similarly, if you see over there, this is also a synchronized operation, and the clear pulse is also given. A single pulse can clear all the data, the past values. But what is the difference? You are giving a serial input and you are taking a output at the end of the operation. Whereas in this case, you are taking the output at every operation of the flip-flop. Right? So it is parallel input, parallel output is a fast mode of operation as compared to your serial input, serial output. And if I say, if you used LAN transfer of data, might be you write in a comment box, how many of you use the mode of operation and the transfer of data using LAN. When you transfer a data using LAN, you're talking about SISO, which is nothing but serial input, serial output. But on the other hand, if you talk about USB, if you're talking about some large amount of data to be transferred, chunk amount of data to be transferred, is parallel input, parallel output. I hope this is clear. So this amount of data, this is a modus operation only, but we have our memories also. And these memories are now a part and parcel of our life. We cannot go away or avoiding these memories. We cannot say, okay, we have memories, even though CSE students especially, see, they are using large amount of data, and I just leave to you, you can write in a comment box. In one of the placement interview, one of the interviewer asked a student what amount of RAM and what amount of ROM you used. And in a reply to that particular question, a student told that sir, I am using 1 GB of RAM and 2 GB of ROM, and straight with the interview said, okay, thank you, you can go. So see, nobody is going to ask you a question that yes, what is RAM, what is ROM? They are interested that whether you know about RAM and ROM or not. So today in this lecture, in this video, we are going to discuss a little bit of giving an insight about RAM and ROM or different types of memories, which are nothing but your semiconductor memories. We will discuss about classification as well as the application of these memories. We will also understand what is the segregation, how these memories, where these memories can be used, and how their application, how their operation performance can be enhanced. That also need to be understood. So semiconductor memories, in which we are talking about volatile and non-volatile. I hope you understand the meaning of volatile, which is random, which is easily available, which is easily accessible. Various definitions you can check. So semiconductor memories are basically segregated in two ways: volatile, non-volatile. And in volatile, we are having a RAM, which can be your SRAM or DRAM. When I talk about SRAM or DRAM, I'm talking about static RAM and dynamic RAM. In your laptop, the laptop what I am using right now, it is having a DRAM. SRAM we can also have, not a problem. But I am having a laptop right now, which is having an AMD processor. And India, we normally don't use AMD processor. We are normally use Intel processor. I'm leaving you with a question that why this is. Okay, and nowadays we are using AMD also. But why it was not popular earlier? Please answer me in the comment box. Definitely, I will answer you in the comment box if the answer is not right? So volatile, yes, SRAM and DRAM. And in semiconductor memories, we are talking about non-volatile, where we are having a ROM and flash memory. Where the flash memory is incorporating your NAND and NOR configurations. But in ROM, we are having a PROM, programmable ROM, EPROM, and EEROM. If I talk about memory, you have to see over here from the CSE point of view, from the electronics point of view, from the electrical point of view, from the automobile point of view, or mechanical point of view. You can see we are having a CPU, we are having a ALU. We know what is CPU is, central processing unit. We have some chipset which contains several controllers. Okay, the memory controller, you know very well the part of chipset, and I'm not going into deep into chipset, what is chipset and what is bus, but yes, I just want to say the bus is basically transferring information from one point to another point. And these all are done on the motherboard. So we are having memory bus. This is basically a diagram which is showing that yes, how this different connections, Ethernet. Now, most of the students are not knowing about Ethernet and internet. They're not knowing that what is the difference between both of them, whether they're using IP4 or IP6. They're the basic things, beta. Right? Please answer me in the comment box. If you're not clear, I will make a video on this with the basics for computers and we'll discuss with you. The memory, semiconductor based integrated circuit, you can check out. We have a CPU register. Then we have a cache memory, which is basically to use to reduce the mismatch between your keyboard and the computer speed, because they are not matched. One is analog, one is digital. Okay, so cache memory, level 1, level 2. Then we have a RAM memory. It can be physical memory, it can be virtual memory. Right now, nowadays we're talking about more about virtual. Whether it's cloud, whether it's grid computing, whether it's cloud computing, whether it's ubiquitous computing, whether it's fog computing, right? So I hope you are aware about fog and cluster computing and cloud computing. If you're not, just see my previous videos. I discussed about the difference between fog computing and cloud computing. We have different storage devices in which we are having a ROM, BIOS, basic input output system, then removable devices, and this we are having USB, the networks, internet storage, and hard drive, that is permanent storage device. Right? You can see that mass storage devices, you can see removable media drive, your removable medium, central processing unit, which is having a registers and cache memory. And the registers, combination registers capacity depend upon the type of processor we are going to use. Then we are having input sources in which we have a keyboard, mouse, movable media, scanner, camera, remote source, or other sources. Any desk you are using sometime. So these are also having some kind of memory. And just simple question: why your system hang? Just see somewhere every process is given certain amount of time. P1, P2, P3, P4 that you will study in operating system, but I'm just giving an overview. When this processing time overlap, then your system hangs. Okay. This is a memory structure. Again, the repetition of this. So you can check out the memory is volatile, non-volatile. You know very well. Then ROM and RAM can be seen. Then you know very well ROM. Then flash you are having NOR and NAND, and hard disk, CD, DVD, the drives are also one kind of memories. Again, just see this is not clear to many students. When I say 64K, how many memory allocation it is having? It is having 1K is nothing but 1024, so 64 into 1024. And the memory allocation start from 0 to that particular value. Similarly, if I'm having 1024K, I will say 1024 into 1024, these much memory allocations or memory allocations I would have. And these memory allocations would be in RAM. So you can see SRAM or DRAM. In ROM, we are having masked ROM also, in which we tag the values. We have UV EPROM also. Okay, you can use UV as an input source for removing the data. Okay, so it is able programmable read-only memory. So that is your flash memory. Then we have volatile memory. Yes, it requires more power to store information like DRAM, DDR. SDRAM is a dynamic in nature. SRAM is basically cache memory. And you can check what is the maximum value of cache memory we use. It is nearly 10 MB. To best of my knowledge, if you know that cache memory, more cache memory value, you can write in a comment section. Okay, but what up to my knowledge, it is available till 10 MB. So we know that what is the difference with DRAM and SRAM? See, the DRAM consists of tiny capacitors that leak electricity, but in SRAM we are using flip-flop. That is very, very important. Very, very important. In SRAM we are using D flip-flops that you are incorporating in the traffic lights also. Again, DRAM require very few milliseconds, but SRAM hold it constant as long as the power is available. Now I think you got your answer. One of the students asked me the question, sir, SRAM is good or DRAM is good, right? So for when you're talking about control S, right, when you're doing the data is removed. Here the difference between SRAM and DRAM clarify. DRAM is inexpensive, but SRAM is very, very expensive because it has to store certain amount of data for certain amount of time. It is slower than SRAM. SRAM is very fast, but it is very expensive also. It is made normally in cache. Cache memory is basically SRAM. Okay, many bits per chip, cannot store many bits per chip. Uses very less power, uses very more power in SRAM, generate less state, but it generates very, very a good amount of it in SRAM. So DRAM is main memory, whereas SRAM is for cache. For cache is memory. Now our research is going on. I expect many students to do the research in this area also. This area is basically known as VHDL, and you can search out what VHDL is all about. And we have many labs in India also which are working on this area. Non-volatile, we are talking about non-volatility and the stored information. So we know that electrically addressed ROM, electrically addressed means electrically can be erased also. Programmable read-only memory, masked ROM can be there, EPROM can be there, the electrically erased program read-only memory can be there, and the flash memory. Mechanical address system we have, it can be tape hard disk, it can be optical disk, CD, DVD, you know very well. Most of the, how many, just write in the comment section, how many of you already knew that your CD and DVD are basically optical disk or magnetic disk? When we talk about magnetic disk, we talk about floppy disk, and when we talk about optical disk, it is CD and DVD. Then we are having a ROM, read-only memory. Very crucial information that is required. So that crucial information essential to operate the system we use with to boot the computer. Right, it is not volatile and retain its data. Different types of it using calculator and peripheral devices. This is very important. This is normally asked in through Venn diagram also. So you can see that in EPROM and EEPROM, electrical erased PROM and EPROM, the flash is basically another kind of memory, and DRAM and ROM somehow, somewhere can be integrated, can be clubbed together. So in the case of flash memory, it is very good, highly reliable, low power, high speed architecture, but very difficult to make. Very difficult to construct or make to increase its retentivity. In DRAM, yes, high density, low cost. SRAM is a key feature in the memory area now. Most of the researchers are working in SRAM. So in this video, we discuss about memory allocations, we discuss on memory interfacing, we discuss about counters, we discuss about different types of structure, different configuration for the counters, even though for the memory architecture, right? So what we comprises digital electronics, what we understand from this video, I hope you understand that how the memory can be used, what are the applications of memory, how can we segregate the memory, and how can we use the counters for different applications. This is all from this video. I hope you like the video. If you like it, then you can subscribe this channel, and you can also go ahead with this channel. You can share this channel. I'm making the video as per the requirement of the students, so you can also check out other videos which are of good value to your curriculum and to your knowledge. Thank you very much.